Hey everyone, and welcome to this explainer. If you're a focused learner looking for a crystal clear, highly structured breakdown of the climate crisis, well, you've landed in exactly the right place. Today we're going to unpack the mechanics, the impacts, and the economics of climate change. We're cutting through all the noise to look directly at the science, the hard data, and the real-world consequences, breaking down this incredibly complex topic into simple words.
Okay, let's dive right into this. We're structuring this just like an environmental engineering syllabus today, following a 5-step roadmap. Number 1, defining the crisis. Number 2, the greenhouse effect explained. Number 3, environmental and weather impacts. Number 4, human health and vulnerability. And finally, number 5, the global economic cost.
All right, part 1, defining the crisis. Let's lay down the foundations of environmental science.
So to truly understand the complex global impacts we're going to discuss, we absolutely have to get our baseline definition right. Climate change is defined as a long-term change in average weather patterns. And I really want to emphasize those words, long-term and average patterns. We're not just talking about a single, unusually hot day or a random rainy week. We're talking about persistent, systemic shifts in temperature, wind, and rainfall that literally define our local, regional, and global climates.
Now, this brings us to a super common point of confusion that we need to clear up right off the bat: weather versus climate. Mark Twain famously quipped, "If you don't like the weather in New England, just wait a few minutes." And that perfectly captures the whole concept of weather, right? It's local, and it happens over really short periods, minutes to days. Climate, on the other hand, is the long-term regional or global average, usually measured over a period of at least 30 years. To put it simply, weather is your current mood, climate is your overall personality.
Similarly, you've probably heard the terms global warming and climate change tossed around interchangeably all the time. But honestly, they aren't the exact same thing. Global warming refers exclusively to just one single parameter, Earth's rising surface temperature. Climate change is the overarching umbrella term. It definitely encompasses that temperature rise, but it also includes the resulting shifts in wind, precipitation, and a bunch of other compound environmental factors. Global warming is really just one piece of the massive climate change puzzle.
Moving on to part 2, the greenhouse effect. Let's get into the atmospheric physics.
To explain the core cause of all this in simple words, NASA uses a really brilliant analogy. Just picture a literal glass greenhouse. Step 1. Human activities, mainly burning fossil fuels and cutting down forests, release massive amounts of specific gases. Step 2, these gases start to accumulate up in our atmosphere. Step 3, these accumulated gases act exactly like the glass of a greenhouse. They allow sunlight to pass through and warm the Earth, but they block that heat from radiating back out into space. The heat gets trapped and the entire planet warms up.
So what exactly are these gases acting like that greenhouse glass? Well, the key players are water vapor, carbon dioxide, methane, nitrous oxides, and chlorofluorocarbons. Carbon dioxide, or CO2, is the big one we always hear about because burning coal and oil aggressively increases it in the atmosphere. To give you an idea of the sheer scale and speed we're talking about here, data shows that in just a recent 12-year window, the amount of CO2 in our atmosphere spiked by an astonishing 30%.
Which brings us to part 3, environmental and weather impacts, basically the physical dominoes. Now, what's really interesting about this text is the definitive language used by the world's leading climate scientists. The Intergovernmental Panel on Climate Change, or IPCC, states that human activities have unequivocally caused global warming. Not likely, not possibly, but unequivocally. There is absolutely no scientific ambiguity here whatsoever.
And here is the stark number that proves it: 1.1 degrees Celsius. This is the exact global surface temperature increase above pre-industrial levels that was observed in the decade from 2011 to 2020. I know it might sound like a tiny number, just over 1 degree, but on a planetary scale, that amount of extra thermal energy represents a massive, massive disruption to Earth's systems.
The science brilliantly illustrates how that single degree just knocks over a whole line of physical dominoes. According to the World Meteorological Organization, warmer air holds more moisture, specifically about 7% more for every 1 degree Celsius of warming. This directly leads to an increase in heavy, concentrated rainfall where literally months' worth of rain falls in mere hours. At the exact same time, this trapped heat creates what the WMO calls compound disasters. We're talking concurrent heat waves, severe droughts, and massive wildfires happening simultaneously, right alongside rising sea levels and increasingly intense Category 4 and 5 tropical cyclones.
All right, part 4, human health and vulnerability. Let's pivot and look at the biological cost of all this.
Consider this staggering figure for a second. 3.6 billion people. That is nearly half the entire global population. According to the research, this is the number of people who currently live in contexts that are highly susceptible to climate change. This threat isn't some sci-fi scenario in the distant future, it's the current, everyday reality for billions of people right now.
And the toll on human life, it's severe. The World Health Organization projects that between the years 2030 and 2050, climate change is expected to cause approximately 250,000 additional deaths per year. That's 250,000 extra lives lost annually, directly stemming from the environmental disruptions we just outlined.
To really understand how those environmental hazards translate into health crises, we can break down the specific threats into categories. Under water and food, we see extreme hazards like diarrheal diseases from flooded sanitation systems and severe undernutrition from crop failures. Under vector-borne, shifting climates are actually allowing diseases like malaria to spread into totally new regions. Direct environmental threats bring lethal heat stress and physical harm from wildfires. And we definitely can't ignore mental health. The anxiety, the PTSD, and the deep trauma resulting from displacement and losing your home to extreme weather.
But here's an absolutely crucial takeaway. These impacts are not felt equally. Over the last decade, human mortality from extreme weather events was 15 times higher in highly vulnerable regions compared to less vulnerable ones. There is a stark, undeniable inequality here. Low-income countries and disadvantaged communities, often the very people who have contributed the least to global greenhouse emissions, are the ones suffering the most severe, fatal health consequences.
And that leads us to our final module, Part 5, the global economic cost, how this destabilizes our finances and infrastructure.
$38 trillion. That's the massive estimate calculated by the Potsdam Institute for Climate Impact for annual global economic damages by the year 2050. Just let that sink in. $38 trillion every single year bleeding out of the global economy due to lost productivity and completely ruined infrastructure.
So where exactly does that $38 trillion loss actually come from? Well, from massive economic disruptors. We're seeing plunging labor productivity because it's literally becoming too hot for people to work safely outdoors in agriculture and construction. We're seeing the destruction of coastal infrastructure and ports, which totally isolates our supply chains. And we're seeing the insurance markets completely buckle, with soaring premiums and properties in high-risk areas becoming entirely uninsurable. This forces governments to spend their limited budgets on emergency disaster aid rather than investing in long-term economic growth.
It turns out the relationship between a healthy environment and a stable economy is completely symbiotic. As this quote from the financial advisory firm Baker Tilly highlights, the bottom line is that acting now to build resilience and cut emissions will cost far less than dealing with the long-term economic damage of inaction. The economic case for urgent policy is exactly as strong as the environmental one.
So, knowing the mechanics, seeing the profound impacts on our health and our homes, and understanding that massive financial cost, it leaves us with a choice. Will we invest early in resilience and mitigation, or will we choose to pay the catastrophic price of delay? Thank you so much for joining me for this explainer. I really hope this structured look at the data has helped bring some clarity to one of the most complex issues of our time. Keep learning, and I'll see you in the next one.